Hey folks, a couple quick words before we start the show. This show is a partnership between Canary Media and Postscript Media, and our partners at Canary Media need your help this giving season. Financial support from listeners like you is critical to Canary's newsroom. Any tax-deductible donations you make go straight to funding their award-winning journalism on the solutions of climate change, on energy equity, workplace diversity, and so much more, including this podcast. Donations help grow Canary's reporting operations so they can continue to tell more stories and investigate more leads. Go to canarymedia.com. Click on the donate button to give a gift today. Thank you so much. Also, just one more word about our survey. We've been asking you for your input on our shows, and we've got a link there at the top of the show notes. We are going to be giving away 5 $100 Patagonia gift cards if you end up leaving your email address. That is optional, but we would appreciate it if you could give us some feedback. It helps us so that we can structure the show to better meet your needs. Thanks. Here's the show.
From the studios of Postscript Media and Canary Media.
I'm Shayle Kann, and this is Catalyst.
The reason why these resistance-heated electric thermal storage things are only emerging now is that it's only in the last few years where intermittent electricity has become the cheapest form of energy that humans have ever known in civilization's history.
Industrial heat. So hot right now.
Catalyst is brought to you by CohnReznick Capital, a leading renewable energy investment bank servicing the U.S. sustainability sector. With the passage of the IRA and the global shift towards greater ESG investing, expert financial advisory services are more crucial than ever. Learn more about how CohnReznick Capital can help with your project finance and M&A needs by visiting CohnReznickCapital.com. Catalyst is supported by Scale Microgrid Solutions, your comprehensive source for all distributed energy financing. Backed by Warburg Pincus, Scale gives developers more certainty and simplicity in the financing process. They're investing hundreds of millions of dollars into solar, energy storage, microgrids, EV infrastructure, CHP, and more. Their unique technical expertise allows them to pull projects over the line, no matter where they are in the development process. Distributed generation can be complex. Scale makes financing it easy. Visit scalecapitalsolutions.com to learn more.
I'm Shayle Kann. I'm a partner at the venture capital firm Energy Impact Partners. Welcome. So one of my favorite things about climate tech is how full this sector is of these unsexy categories that have this ridiculously enormous scale and impact, where potentially relatively simple solutions can solve a huge climate problem. Case in point, industrial heat. Industrial heat is the single largest source of greenhouse gas emissions in the world. Full stop. I will pause there. It is responsible for more emissions annually than all transportation globally put together. About 25% of all of our emissions come from burning fossil fuels to generate either heat or steam to power some kind of industrial process. One of the reasons that we don't talk about it as such very often is that it crosses sectors. So we do talk about decarbonizing things like steel and cement and chemicals, but in each of those cases, much of, or in some of those cases, all of the emissions really is just coming from the production of heat. But of course, industrial heat is not just one thing. We need it in different forms, at different temperatures, for different processes, integrated in different ways. And above all, we need it cheap because that is how it is delivered today. So how do we do that while decarbonizing as fast as possible? That's our question of the day. And I was joined for this one by John O'Donnell, who is the CEO and co-founder of EIP portfolio company Rondo Energy, which, as you will hear, is tackling this problem of decarbonizing industrial heat head on. Here's John. John, welcome to Catalyst.
Thank you for having me. It's a pleasure to be with you.
Let's talk industrial heat. And let's start at the high level. So walk me through, why do industries use heat? And what's the right way to think about sort of categorizing the different industries and the ways that they use heat differently?
Great question. Let's go up one click more. Half of the world's final energy use is used for heating and cooling. And of that, about 95% of that is heat. Heat used for industry is about 25% of total world energy use, and a little more than 25% of total world CO2 emissions, because it comes from burning coal, oil, and natural gas, more than about 80% of all heat. So for scale, I think the unit is 99 exajoules of industrial heat in 2019. If we do a units conversion and ask ourselves, we want to repower that with renewables, it's about 10,600 gigawatts of renewables, wind and solar with typical capacity factors, needed to replace that fuel consumption. And as I think, as everyone knows, we're at a spectacular moment in world history because those renewable electricity sources are now cheaper than the fuel being used today.
Well, so we'll come back to the ways to decarbonize it a little bit later, but I want to spend more time on what it is in the first place and why we do it. So can you explain the purpose of heat in industrial applications? And then again, I want to break it down a little bit beyond, I think you hear there are these like ridiculously enormous numbers for how much industrial heat we use. So let's go one level beneath that and talk about different temperatures, different forms of that heat, and see if we could break it down a little bit.
Sure. Whether you're making baby food or steel or cement or plastic or any of the tangible things that we use, or whether you're making fuel or pasteurizing milk, there's a wide range of temperatures, but across pretty much making everything globally, about 3/4 of the total energy consumed in our economy, which makes stuff, is heat, not electricity. When you're making cement, you mine a rock, you heat the rock literally to boil CO2 out of the rock and reduce the mineral to cement. Typical cement plant might use 55 megawatts of electricity and 1,000 megawatts of heat. Similarly, making steel, making aluminum, making, across all sorts of things, heat-based processes are transformative. And of course, because if what we have is fuel to start with, they are by far the cheapest ways of making those commodities. As a civilization since the Industrial Revolution and before, we've figured that out, right? All the way back from cooking and residential heating at the dawn of human time.
You sort of made this point, but there are different temperatures needed to run different industrial processes. Some relatively low temperature processes will need 100 degrees Celsius, for example. And at the other end of the spectrum, you have stuff like steel making, which is well over 1,000 degrees Celsius. So how does that pie split out?
Yeah. Which technologies are going to be applicable where? And you summed it up. And if we go all the way to the high end of the number, part of making cement is well over 1,000 degrees Celsius. Yeah, pasteurizing milk, we need heat at around 80 degrees Celsius. Making baby food all the way through refining petroleum and biofuels, we need heat at around 200 C. Something like 80% of industrial heat is in the low to mid-range temperatures below about 350 C. And then there's a chunk around 500. Making cement, for example, 2/3 of the energy is at about 1100 C and 1/3 is about 1800. So, and that's really the highest that's in use. Steel making today, making steel with coal in blast furnaces, is at a higher temperature. But as you know, the steel industry is moving to new technologies that don't use coal, that run at different temperatures. They run actually at around 1,000.
Let's talk a little bit about what this actually looks like inside an industrial facility. It's going to vary substantially, obviously, based on what you're making. But just paint me a picture of typical industrial facility that needs, let's just say something that needs relatively high temperature heat, 500 degrees C or above, or something like that. What does it look like? Where is the heat getting produced? Is it fossil fuels being combusted on site with pipes into the rest of the industrial process? What is the actual physical manifestation of this heat?
Up to about 600, the vast majority of heat is moved around as steam. Steam is an excellent heat carrier. So when you walk in, you will see giant boilers, sometimes that are the size of a house, that are combusting fuel and making steam, and then start large insulated steam pipes running to the places where heat is used. In a food production facility, you might see 6-inch steam lines. In a refinery, you might see steam lines that are 2 feet or larger in diameter. For higher temperature processes, making cement, for example, heat's used in a different way. You'll see large, giant tubes that are rotary kilns, and combustion of fuel is happening inside the kiln. So there are heat applications where the fuel is combusted in contact with whatever it is that we're making. And then you call those direct heating systems. And then most heat is indirect. That is, there's combustion and then something that transfers the heat to whatever that you're cooking or melting or, yeah.
This is one of the things that I wanted to get across is that it's not monolithic. Different industries, different industrial processes will use heat in different ways. They will use it integrated into their processes in different ways, and they will use it at different temperatures and in different forms. As you said, sometimes direct process heat, sometimes it'll be in the form of steam and so on. So it's a massive category, but it's not one thing, right?
Yes, that's right. Again, sometimes it's heat is transferred by a fluid, sometimes it's transferred by steam, sometimes it's transferred by air, and sometimes it's radiation, thermal radiation from combusting fuels directly in whatever that process equipment is.
We've talked a little bit about the fact that the reason this is a ton of emissions is it's mostly combusting fossil fuels right now. What generally dictates which fossil fuels we are combusting in current industrial heat processes? Is it just whether a given location has access to coal versus natural gas, or is it a function of the process itself?
That's a great question. For the vast majority, I think the answer is the former. That is, what is the historical, especially, and present availability of energy in what form? And also, what's the scale? You don't find very many small coal-fired things. Because of all the difficulties with emissions control and the complexity of coal combustion. Large things in some places in the world are fired by coal. Natural gas, its huge expansion in availability for the last 20 years has really been moving. Industry has moved off oil and moved off coal and onto natural gas around the world. Of course, in some places in the world today, in addition to the climate crisis that the fuel use is driving, there's a gas supply crisis in particular that's causing great disruptions for industry.
All right, so we've got this massive category of energy consumption, corresponding massive category of emissions. Not monolithic, but it shares common characteristics, those characteristics being the need for heat at various temperatures and in various formats. So let's talk about how we get rid of those emissions. How do you think of the kind of high level? Like, what are the categories of potential decarbonization solutions for industrial heat?
Yeah, great question. The first test that we have to apply to every one of these categories is, what does it cost? Because for a lot of these industries, the things that we're talking about, whether it's making baby food or cement, this is not making computers where there's a large gross margin and energy is a small portion of the cost of production. We're talking about commodities where the margins in the business are small, and energy in some cases is 40 or 60% of the total cost of production. So the number one thing about all the sources is, what do they cost? Second, of course, is how available are they? And that tends to be by location. And then, as you've said, all right, what are the temperatures? What are the needs of the process? So if we wind back from that and ask, all right, what are the options to a zero carbon energy infrastructure for industry? One of the things that in some places you can do right now is buy biogas instead of renewable natural gas. There's a very limited supply of biogas. It's being aggressively taken up, and it sort of typically trades at about a 4 times price premium to natural gas. So in some places where it's available with no change to anything at your facility, if you're willing to accept a big cost increase, all right, that's one pathway. Another pathway that involves very limited modifications to your facility is beginning to substitute hydrogen for the fuel that you're burning today. Burners can be adapted, boilers can be generally adapted. And now everything, of course, depends on what is the source of that hydrogen, what does it cost. Hydrogen is, of course, very attractive because it can be used all the way up to the highest temperatures, including in internal combustion systems, making it from clean electricity. It's about 2 units of electricity for 1 unit of heat. The production equipment, the electrolyzers, are expensive today and they're coming down in cost. That 2-to-1 ratio, though, is not something that's going to change. That's really driven by physics. So that's one option. And today, of course, that is substantially more expensive than the biofuel option. But government policies, developments, they're going to drive that down. Using for the low temperature processes where continuous electricity is reasonable priced. And when I say low temperature, I mean up to about 110 C. Heat pumps are quite attractive because a heat pump, unlike hydrogen, where it's 2 units of electricity for 1 unit of heat, a heat pump can take 1 unit of electricity and give you 3 units of heat. The heat pump, the hydrogen system, can operate intermittently when the sun is shining and the wind is blowing and give you continuous heat from burning hydrogen. The heat pump, by contrast, needs to run all the time, but it's very efficient. And then there's this new class that Rondo and others are working on, this new class of systems that have really only emerged in the last couple of years of just using electrical heat directly, electrical resistance heat, just like your toaster, storing that heat. So heat when the sun is shining or the wind is blowing, store that heat and deliver continuous heat. Now, and the temperature range and applicability of that actually now goes up to about 1500. Doesn't go up as far as hydrogen. There's maybe 5% of industrial heat that it won't apply to, but it's about 1.1 units of electricity per unit of heat and lower capital cost than those other options. So now, which of those is lower cost? I said the thing that's most important is what is the cost? That depends on what are the dynamics of renewable electricity in that location. The reason why these resistance heated electric thermal storage things are only emerging now is that it's only in the last few years where intermittent electricity has become the cheapest form of energy that humans have ever known in civilization's history, right? That's true today. And so this new class of electric thermal storage can play a role into tapping into that.
Right. So let's draw this out a little bit more. First point that I think is embedded in what you're saying, but is important to note, is that basically actually, you tell me if this is true. Basically, every industrial process needs to operate 24/7.
That's almost completely true. I mean, we talk to cheese factories and dairies that operate, 5 days a week and they don't operate on the weekends. But every large industrial process, that's absolutely true. You start up a smelter or a refinery, if you turn it off, it can take you weeks to restart it. So yeah, they operate typically with one annual shutdown for inspection. So yes.
Right. Which is a key point, because if that were not true and electricity, if you could just operate whenever there's cheap power economically and technically at these facilities, then they could just use those electric resistance heaters, the toasters, as you've described, directly and get their heat straight from the grid. And they would have no need for anything sitting in between, like thermal storage, like what Rondo's doing, right? But the challenge with that is that, and you can do that technically today, right? There's nothing stopping you from a technical standpoint from just electrifying industrial heat. It's an economic problem, right?
Yeah, it's an economic problem, and a bit it's a technical problem, because you're absolutely right. And I should have mentioned that option, direct electrification live with electrical resistance heaters. There is a whole class of things like electric arc furnaces that also directly use electricity. And an electric boiler, you can pair it with a gas-fired boiler. And there are companies out there who've been doing this for a little while now, setting up software so that the electric boiler runs when the electricity price is X and the boiler runs at other times. That works just fine. But the upper limit that we typically see in the United States anywhere is that maybe you'll get 30% of the hours of the year of clean power. You might get as much as 40% of the hours of the year of low cost power. But so it's a solution that's on the margin interesting. It is not an answer to get 95% or 90% reduction. And it is, so it's much lower cost from a capital cost, and it's mature technology. Electric boilers have been around for a long time. And if you're in northern Quebec, or you're in lots of places in the world where there's a ton of hydropower, that's your answer, right? But the thing that you can have at arbitrary scale everywhere in the world is wind and solar. And in those domains, this matter of, do I want a small portion or do I want the majority of my energy to be renewable? That's the limitation with those systems.
Support for Catalyst comes from Kohn Capital, whose experts have been driven by their passion for ESG and sustainability since day one. Whether helping solar and storage developers raise capital, optimizing structures for carbon capture projects, or helping investors navigate their way through the ever-evolving sustainability sector, Kohn Capital stands ready to help clients power forward. Shayle Microgrid Solutions does a lot more than build industry-leading microgrids. Combined with their technical expertise, Shayle finances and acquires distributed energy projects of all sizes. Backed by Warburg Pincus, Shayle takes an integrated approach to distributed energy financing, setting up developers for success by creating more certainty and simplicity in the financing process. At Shayle, the engineers, designers, lawyers, accountants, and project finance experts all work under the same roof, which cuts out intermediaries that add complexity, risks, and costs for developers. Distributed generation can be complex. Shayle makes financing it easy. Visit ShayleCapitalSolutions.com to learn more.
So what you're stepping in and solving for is this two-sided problem. On one side, you've got the industrial facility, and we're trying to solve for the industrial facility having to change nothing about its operations. That is important. We're not trying to reinvent how they do what they do. They just need heat, and they need heat basically 24/7, 365 or close to it, and they need that heat to be cheap. On the other side, we have a newly cheap source of energy, which is renewables, which are electricity generation devices that, as you said, are the cheapest cheapest energy known to humankind in history, but operate intermittently. And so if you want to take advantage of that intermittent cheap power and deliver it as continuous high temperature heat, this is where something has to step in between, and this is where companies like Rondo are stepping in. Now, what are the characteristics that you need in order to bridge that divide, both technically and economically, sort of being the key point? Because obviously, if you're going to suck up electricity from intermittent generation on one side, from just the hours when the power is cheap, as you said, that might be 40% if you're lucky. So you got to take in electricity at a higher rate during those times so that you could deliver it continuously at the rate that the industrial facility needs at the other side. So as you started to sort of recognize this problem, what were like this is what it's going to take for this to make sense?
Yeah, you nicely summarized it. I say there are three separate problems. Perhaps you could break it down. McKinsey is running this we're working with a group called the Long Duration Energy Storage Council, which just yesterday at COP27 published a report that really actually lays out these matters. So the first of those is, what is the rate and the cost at which you can take electric power, and what's the cost of doing that? How fast can the storage charge? What you find everywhere in the world is that the hours of curtailment, the hours of super cheap power, are much shorter than the solar day or the wind day. You might have 8 hours a day for PV electric power, but 4 hours a day when prices go to zero because there's curtailment. So one characteristic of a thermal storage system is, how fast can it charge? What is the cost per kilowatt for the charging system? The other matter is, now, how is the heat delivered? How adaptable is that? And different storage systems, based on how do they store energy in the core, what does it cost to convert whatever that heat is to hot water or to steam or to superheated air or superheated CO2, depending on what you're connecting to. What is the cost of that output energy conversion? And then, of course, what is the cost of the core, and how do we store energy? I mean, put a stone in your oven, heat it up, take it out, wrap it in blankets, put enough blankets on, it'll be hot a week later, right? And there's a great thermal energy storage technology. And there are a bunch of folks who are doing variants of rocks in a box, whether it's crushed gravel or sand or other aggregate material. What you find when you pull on that thread is the box costs lots more than the rocks. There are very interesting applications there. They tend to be somewhat limited in the temperature they can reach because they have some external heating thing, and the cost of that heating thing for fast charging may be an issue. There is a lot of work, there has been work for 40 years in storing high temperature heat in liquids. Fertilizer, sodium nitrate, potassium nitrate. If you heat them up to about 180 C, they melt and turn into a colorless liquid that's stable up to about 600 C. Those molten salts have been widely used in the solar industry for providing heat storage. They top out at 600 C. They have lots and lots of cost and engineering issues, but that's another class. There are a lot of new materials that folks are working on, using storing heat by melting and freezing silicon or aluminum, storing heat by superheating graphite and keeping it in an argon or a krypton atmosphere. What Rondo is doing is, we looked around when we started Rondo, because we've been working on these industrial heat matters for a long time. Previously, a bunch of us delivered more than half of all the solar industrial heat that's running now. We've been looking for storage things. The steel industry for 200 years has had waste heat storage running at scale. There's 300 gigawatts of heat storage running right now at the blast furnaces around the world. They store heat in brick. They figured it out in 1828. Rondo is, we're using that material because it was proven, because it was available. And we came up with a way of heating that lets us heat faster. But this entire class of solutions, every one of them is above about 95% efficient in capturing electricity and delivering continuous heat. Based on what's in the middle, is it a liquid like salt? Is it a solid that you're an aggregate that you're blowing air through? Or is it something that's melting and freezing? The way it connects to the output process is somewhat different, but they all have those same characteristics. What's it cost to charge it? What's it cost to hold it? And what's it cost to deliver it?
Greater than 95% efficiency is one of these key points that I think is important to reiterate, because we're used to thinking of storage. I mean, most people are used to thinking of storage as being batteries. Very few batteries can approach 95% efficiency. This is a different context where actually you don't lose a lot of the energy when you're just turning electricity into heat, storing it as heat, and delivering it as heat. Now, if you were to try to turn that heat back into electricity again, and use thermal energy storage for electricity storage purposes, which some companies have also done, you would lose more in that reconversion. Heat to power has a conversion efficiency loss. But again, what we're trying to do here is just electricity to heat, stored as heat, delivered as heat. And it's actually remarkably efficient when you do it that way. The other thing, as I learned about Rondo, that I came to appreciate is that it also, we talked, you said this is McKinsey's thing is the Long Duration Energy Storage Council. When we think about things like long duration energy storage, the other thing is you don't really lose a lot of heat over time. This is what you were describing with the rock that stays hot. If I put it in my oven, or if you're trying to create like a hot stone massage, you'll discover that these rocks stay hot a pretty long time. How much do you lose if you just let the heat sit there as heat for an extended period of time?
That's a great question. I want to come back to your efficiency thing first and then talk about the heat storage for a moment. So a very large portion of industrial heat today is delivered in combined heat and power things. That is, somebody runs a boiler, they run a high pressure boiler, they run a turbine, which is only partially efficient at converting heat to electricity, but the waste heat from that turbine then runs the process. These CHP, or combined heat and power systems, the U.S. had a huge regulatory push back in the 1980s. A lot of industrial heat's delivered that way. And the remarkable thing is when we get rid of the boiler in the combined heat and power system, when we use any of these thermal heat storage systems, now we still have about 95% input to output efficiency, where we're taking intermittent electricity and we're now delivering continuous electricity and continuous heat. You're right. If we don't have a use for heat, then any system that generates electric power is going to be, on the order of 45% efficient or less, running through a thermal storage system. That happens to be very similar to the efficiency of some of the other long duration electricity storage systems. But if we're thinking about long duration electricity storage, then we are addressing the matter that you mentioned second, which is what happens when I keep it bottled up for an extended period of time. If we go back, the main problem that we're trying to solve is run that factory 8,700 hours a year. And from intermittent electricity, there's no business reason for using very much long duration storage. That is, especially in wind places, there are periods where you get 2 weeks where the wind isn't blowing. But, one of the really remarkable things about this application, if you think about it, what happens when renewable electricity isn't there in the power grid? You're burning fuel in conventional power stations to back it up, and it's about 50% fuel efficiency doing that backup. What happens here if we're running heat into a facility? When I'm backing it up, when the wind's not blowing or the sun's not shining, it's about 90% efficient because I'm running a boiler, not a power station to back it up. And that says that we don't see a business reason for storage beyond about 20 hours of storage. That if you have about 20 hours of storage, there's going to be about 10 or 12% of annual energy that you're going to get from something else. Whether that's in the purely renewable world later on, that's hydrogen. In the meantime, that's fuel. And so without, when you get to about 20 hours of storage, in this use case, you don't need much longer. But you're right, in principle, these thermal storage systems, they have the long duration energy storage that has the lowest loss, of course, is hydrogen. If you want to move energy from July to January, don't use something that self-discharges over time. Don't use lithium ion. So the problem that we're solving, though, is the least cost industrial heat.
So obviously the limiting factor on doing this at scale is going to be access to that really cheap, clean electricity. You need either to have a grid connection somewhere where the power is clean some of the time, clean and very cheap some of the time, or you need to have the resources directly, right? Wind or solar nearby at the scale that will power an industrial facility, which is big, generally speaking. So this isn't like you can't, we're not talking about rooftop solar here. We're talking about tens of megawatts, hundreds of megawatts, maybe gigawatts for facilities. How do you think about that limitation and relatedly between those two options, the build nearby cheap, clean renewables versus grid connect and just charge when the power is cheap?
That's a great question. And, there's a dual thing that you mentioned, either local renewables or charge when the grid is cheap. There's beginning to be a bunch of work on kind of sector coupling. Evolved Energy Research just published a piece not too long ago looking at the role of thermal storage in the evolving electricity grid and large amounts of new generation that are serving industrial heat loads that are switchable. That generation will also wind up participating in delivering grid reliability and lowering the cost of renewables. So it's not quite either or, but for starting, yes, absolutely, either or is a good way of thinking about it. And the thing I'll say is people are very good at figuring out and doing at scale what is cheapest, right? The US has built tens of thousands of miles of interstate gas pipelines because gas became a cheap fuel. We are struggling. Steve Chu used to say the United States does electricity today the way we did roads in 1939. We are struggling with longer distance electricity transmission, but as you know, you can move electricity 1,000 miles and lose 4% of the energy in HVDC systems. So as this rolls out, as electrification of industry rolls out, for sure, you're right. The biggest issue is how fast are those wind facilities and solar facilities being built. In Europe's sprint to get off Russian gas, the build out is the big issue. 22% of the wind projects that were proposed in Sweden last year were permitted. Right? There are all kinds of permitting and construction matters. Someone once said to me, why is all the heavy industry in the UK on the coast? It's because where it was cheap to bring the coal. Over time, we're going to see energy intensive industries adapt to where renewables are cheapest. But look, for the next 20 years, it is all about repowering the facilities that we have today. And that matter of, is there a place somewhere within 20 miles where private generation can be built? Are we moving power through the grid? How are we relating with existing tariffs and regulations for grid access? We at Rondo and the entire industry that's doing this is grappling with those matters right now.
Well, you just got to one soapbox that I like to go on, which is exactly related to your point about why all the industrial facilities in Ireland are on the coast. So I'm curious to get your take on this. This is an emerging thesis that I've been playing around with. So as you know, there's been divergent trends in terms of the cost of renewable power on one side and the cost of delivered grid electricity on the other side, right? Cost of renewable power has been going down. Cost of delivered grid electricity has been going up. And that's for two reasons. One is T&D, transmission distribution costs, continue to rise even when generation costs go down. And two is the balancing component of it and the cost of having a bunch of stuff online to deal with when the solar and wind aren't there. If you believe that those two lines will continue to diverge and it's going to continue to get cheaper and cheaper to just build renewable power, but it's also going to continue to get more expensive, at least on a relative basis, to get delivered electricity through the grid. For industrial facilities where the cost of energy, as you said, can be 40, 50, 60% of their total operating costs, and in a world where you have solutions to deliver continuous industrial heat, but using intermittent generation, whether it's Rondo or something else, are we not over some extended period of time likely to see massive scale grid defection, only not the type of grid defection that we talked about 10 years ago where it was people putting solar on their roofs, but instead it's industrial grid defection where industrial facilities increasingly are powered by off-grid renewables? Is that a future that you could imagine happening? And if so, to your point about where these things get placed, like we could end up with, a wave of industrialization in the upper Midwest where there's cheap wind and in the South where there's good solar resources, but independent of where we see all that stuff today, because you remove the transmission constraint from the equation. Like, is this a totally crazy concept?
No, these are the two. This is right at the heart of things. I'm really glad you mentioned all three of those things, because I would agree with you. For sure, we are headed toward huge industrial growth in the upper Midwest and the whole corridor from, the Dakotas down to the Panhandle. Oklahoma had 2,000 hours last year of negative wind prices. The IRA is going to bring vastly more of that intermittent negative price everywhere in the country. The production tax credit is tied into that economically. Now that's coming to solar. It is remarkable. Falling cost of generation, yet rising cost of electricity. Like, what's going on? Well, one is, you forgot to mention wind and solar deployments in the United States are slowing down, not speeding up. And there's a 10-year interconnection queue in Oklahoma for new wind projects. The average interconnection time for new utility scale PV projects in California is 7.5 years. So some of what we're seeing is rent extraction. Those who can get connected can charge prices that are not cost-based. I got my thing in the queue. So the answer to those high prices is, of course, high prices. That is, in a perfect market, the market would respond by building lots more transmission capacity. But the thing that's really driving, we've been struggling with for decades, is we used to build transmission lines that were connected to coal plants that ran 100% capacity factor. Now they're connected to wind farms that run at 40% capacity factor. So there's a lot of time when you're not using the wire for the same cost wire. What we see, actually, you set it up right. That is, are we going to see big local generation and defection from the grid? What we're seeing, and not surprisingly, is a small company with, we're very impatient. Right? We're working on what can we execute right now. A great deal of what we're doing is off-grid generation. We've built our particular heat batteries to manage off-grid wind farms, off-grid solar farms. There are interesting things involved in doing that. But the medium term is we see a ton of new generation that's going to be built where during those peak hours, right, the peak hour, the actual system peak is about 4 or 5 hours that we see curtailment in California that's coming both from load mismatch, but also from transmission. During those periods, these new generation assets are going to output nothing to the grid. In fact, they may be buying from the grid. But during the shoulder periods, where we need a ton more in the shoulders, they're going to be releasing power to the grid, or they're going to be releasing during grid emergency. And that kind of oddly, the challenge of industrial heat is going to be creating solutions for the grid. And conversely, the challenges of the grid are creating the least cost decarbonization pathway for industrial heat, because we have these really fast, cheap charging heat batteries that can become this new class of load. We spent a lot of time with utilities exploring, this is now a dispatchable load that's just dispatchable, just like you dispatch generation. Instead of, I need 250 megawatts of dead reliable service from a gas-powered power plant. No, I need 8,000 megawatt hours today. You decide when to deliver them to me. That's a whole different future for the grid. And collectively, it's going to take us time to figure that out. But what I think we see is not defection from the grid, but actually value to the grid because of this stuff.
All right, John, that is all the time we have today. Thank you so much for joining me to talk through industrial heat, a topic that is near and dear to both of us, I know.
Yeah, Shayle, thank you so much.
John O'Donnell is the CEO and co-founder of Rondo Energy. All right, so as always, tell us what you think. Tell us what you think about industrial heat and all the ways to decarbonize it. This is actually a new thing. If you want to tell us and let us hear your voice, you can send us a voicemail. Here's how you do it. Just record yourself on your voice memo or sound recorder app on your phone, and then email us the file. You can send it to catalyst@postscriptaudio.com. That's catalyst@postscriptaudio.com. You can also just email us there if you don't want us to hear your voice. Once again, catalyst@postscriptaudio.com. We do always welcome feedback and thoughts. You can also find the show on Twitter, as long as Twitter continues to exist, at @CatalystPod. You can find me there, same caveat. If you like the show today, go over to Spotify or Apple Podcasts and leave us a rating and review. This show is a co-production of Postscript Media and Canary Media. Head over to canarymedia.com for links to today's topics. There's actually some really good reports on industrial heat that we will link there. And as always, Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and agriculture, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf, mixing by Greg Vilfrank and Sean Marquand, theme song by Sean Marquand. Our managing producer is Cecily Meza Martinez. I'm Shayle Kann, and this is Catalyst.